Make sure we're recording. Yep, we're recording. Okay, so this is approximately where we left off. Like I said, we'll keep this short because we're all busy, and as we proceed forward, okay, with this, we know that there's always going to be one more isomer in an alkene as opposed to their alkane counterparts, just because of how that double bond can be rotated. We left off with this, okay? And one of the things, again, this double bond will restrict that rotation, so therefore you don't quite have as many of those different types of isomers that we've talked about in the past. Now, what I mean by that, okay, this allows for two isomers for butene as opposed to butane. It leads to how you can have one more of those isomers. Okay, so new material. And how these molecules are bonded, as you can see, is certainly going to have a difference on their physical and chemical properties. And one way to perhaps visualize that is picture in general chemistry, okay, and a little bit of use with the periodic table, okay, and we use that this chapter too, and that's the halogens. Why is it that those elements are so reactive, the halogens? And the best way to picture that is look at where their placement is on the periodic table. Okay, so therefore you look at their counterparts like lithium, sodium, and potassium, and especially hydrogen. What makes them so reactive? And where are they located on the table? Your alkali metals, where are those found on the table? Like sodium and potassium. Okay, so in that first column, it's going to do anything it can do to get rid of its lone electron. The halogens are going to do anything that they can do to grab onto one electron. Those are chemical properties, but one of the things that we see happening is these different types of rotations that these bonds are oriented in is certainly going to have an effect on their physical properties. And that's what we're trying to make a point of here. So again, chlorine just wants to grab any electron that it can. Hydrogen wants to get rid of that electron. But there's going to be an exception to the rule, just like many other examples that we saw, especially in naming. And we're going to see just a brief example of that here in just a moment. Okay, so I just want to do this slide and then put, then we'll get to that addition reaction. Okay, so let's go ahead and take a look at this, and I just have a couple things I want to show up on the board, and then that will be it for today. Because I don't want to overwhelm you with some of this content. And it's this content that you see on this slide that's going to help us navigate what's actually happening here, okay? Chemical properties. We've already established that alkanes are not as reactive as those of its alkene counterparts. And why is that? I know you know the answer just like that. Why do these not want to react? Okay, they're stable and they're saturated. As you can see, the alkenes are highly unstable. Let me know when you have this, and I'm just going to, like I said, I would just want to put a couple of reactions on the board just to illustrate what it means that we're referring to on this slide. And I thought we're going to keep it under 10 minutes, but I don't think we're quite going to make it because we're at 5.5 now. Unless I really talk fast and we go through this new material and we go through the different products of those that are reactive, highly unreactive, those that are exceptions to the rule, and those that halogen. That was awful, wasn't it? Yeah. All right. You don't need to write this down, okay, what I'm going to put up on the board, because we're going to see ample examples of it. But we just want to have just a brief introduction to this, and then we'll go a little further in depth tomorrow when we get to these addition reactions. Okay, so what we mean by that is as follows. Okay, so just like when I went through all the organic families, I just would always use 3-carbon compounds. Don't know why, would just always do that. Just for the same reason, for instance, maybe when you're getting ready for volleyball, basketball, or whatever, when you're warming up, is there something that you've just always done it this way because you feel comfortable, like it, and then you always get in that routine so you know it's going to be the same. If it's simple, then you can easily repeat it. Okay, so if I was to write propene down here, okay, what does that mean to you?
3-carbon double bond on the first one.
Okay, now, would we have to say 1 propene? No. Can you?
Yeah.
We can. And why is it that we would say just for the same reason? You can say 1 butene here, but if we put that double bond on the other side, yes, that's still 1 butene, but this is either on the left or the right side. But with that, yes, you can write 1 butene, 1 propene. The only reason that you would ever have to do that is if you saw something like this, though. Okay? But if we saw a halogen derivative on there, then you would have to say 1 chloral, 1 propene. Okay? But if there's a derivative where that double bond is, we're taking the approach, say where that's at. It's understood that yes, it's on the first carbon, but once you put that halogen derivative on there, I just think we're better off making sure that we say where that's at. Okay. So what that slide was saying earlier, which one of these if we changed nothing on here, are both of them going to react? You're shaking your head no, that would be correct. Okay? And why would that be then? Yes, they will not react unless what? Okay? Unless you put this below a little bit of heat or some ultraviolet light, okay? Because these are stable, they're saturated, there is no more bonds that they can hold. The main reason I wanted to put this up here is one of the things we're going to start talking about is that of your reactants, which are either symmetric or asymmetric, okay? What does symmetric mean to you? And we talk about in zoology too when it comes to radial symmetry, and that means it just goes in a circle. But any type of symmetry means you're just looking at a mirror, okay? And in this case, the symmetry is the shape of it, and radial symmetry, it's a circular shape. But when we're talking about these reactants, okay, this is what we call a symmetric. See, you got to be careful when you say that, okay? This is called the symmetrical reagent. The reason I got to be careful when you say that is because there's also an asymmetrical reagent, okay? Asymmetrical means it's not a mirror image, because if we write this out, that's what that really means, because it's diatomic, okay? Same as this, okay? I don't know if you remember when we were doing the alkane reactions, I said, how do you want to see that written? And you said, like this, and that's fine, okay? But this is also now an asymmetrical reagent, because when we split this in half, you don't have the same counterparts on each side like what you do here. And the tricky part about this is the more exposure that you have, water you would think is symmetrical, but it is not, okay? This is not the symmetrical reaction, okay? Again, I got to be careful. This is not asymmetrical, okay? Now, do you understand what I mean when I got to say that? A as in the letter, then symmetrical. Asymmetrical is one word where it's not a mirror image. That's what I'm trying to say when I say I got to be careful when I say this, okay? This looks like it's a mirror image, but if you remember your general chemistry, you can probably tell me why this is not a mirror image. And the reason I say that is, okay, let's look at this. What is that compound? It's a base. It's sodium what? Sodium hydroxide, okay? This, you could say, is hydrogen hydroxide, if you really wanted to say that. I mean, you're not wrong. It's how the molecule splits apart, because as we know, this is +1, that's -1. So you have the hydroxide ion by itself and then the hydrogen ion. So this is what we call the asymmetrical reagent. This is the asymmetrical reagent. This is the symmetrical. And that's how it sounds silly, but that way we're communicating efficiently. This does not need to have a catalyst, so nothing has to be here, and then we just attach that onto there. And yes, you get two products. We'll discuss that later. There's always an exception to the rule. This is one of them. Top one will react, the bottom one will not. One of the chemical properties of this will not react unless you have that or your UV light, okay? One of those two. Hydrogen has to have a catalyst, even though we say that this is very, very stable, okay? And that's going to be one of those little pitfalls, or I wouldn't say tricks, but we just do that just to show you that there's an exception to the rule. So this would be no reaction as it's setting right now. And the reason we say it's an exception to the rule is because I know there's one more, but what are you utilizing for alphabetization in this derivative? The B, this one, the I, this one, the B, okay? So that's an exception to the rule. For some reason, this prefix you use in alphabetizing, these prefixes you don't. This is also an exception to the rule. Okay, we made it under 15. I was going to try to do it under 10, didn't quite make it, so we will catch up to you next time.